Everybody, it's my great pleasure to have Professor Sanjit Seshia give us present the Trust Lab colloquium today. He will be talking about towards verified trusted computing platforms with UCLID5. So Sanjit is the Cadence Founders Chair Professor in the Department of Electrical Engineering and Computer Science at Berkeley. He's an alumnus from our department, has an MS and PhD from CMU, and works in the general area of formal methods for dependable and secure computing. He has many awards to his name. He's also a Distinguished Alumnus Award from IIT Bombay and is a fellow of ACM and IEEE.
Okay, thank you, Supratik, and thanks everybody for coming. So I've heard a lot about the Trust Lab, and I'm glad to speak in the Trust Lab seminar this time. All right, so what I want to tell you about today is work we've been doing over the past 10 years on applying formal methods to gaining higher assurance in the kinds of trusted hardware-software platforms that have arisen over the last decade and have grown in popularity. And this is joint work I'll be speaking about with many great students and colleagues and postdocs and collaborators over the last many years. Okay, so just to start out the setting for this work, I think we're already in this era of cloud computing and where we are using various forms of secure remote computation. So the setup here, of course, is that as on the left, we are users or clients who are interacting with applications running in the cloud. And more concretely, I know tax season just ended in India, and of course in the US and around the world, many people use and pay for applications that run on a remote server to prepare their taxes. Now, if you imagine an application like that, you are sending over your own data, some of it may be public, some of it might be private, over to this application running in the cloud, and it has to compute your taxes accurately, right? And maybe there are different types of software you can pay for, and you paid for something and you want to make sure it does the right thing. It computes your taxes accurately, and it's the one that you paid for, right? It's the program that you paid for. And so you might have these sorts of questions in mind, right? I'm sending my secret data over to the cloud. Is that secret data remaining secret as I send it over? I'm running some application there. Is it executing as it's supposed to? Is there a problem? Should I unmute myself? Muted by host. Okay. So can people hear me now? Is it recording? It must be, at least WebEx is saying that it's getting recorded. Okay, good. So for those who missed this and not in the room, I just talked about the setting of secure remote computation and an application for something like tax preparation where people might have these questions, right? I'm sending secret data to the cloud. Does that remain secret? Does the program that I want to be executing on this data in the cloud execute as it's supposed to? And is the right program being executed, right? Okay, now of course, in the context of security, it's always important to ground yourself in a threat model. And there's a whole range of attacks that are possible, right? So classically, there's been a lot of work on looking at attacks on the network level, right? So there are protocols, and the adversary could be in the network and is observing network traffic as it passes and trying to uncover secrets that they're not supposed to know. But of course, we're also very much familiar with attacks at the software level, right? So application level attacks at both the user level as well as the system level of software, which I'll together call software infrastructure attacks. And then there are, most recently, there's been growing interest in looking at hardware attacks, right? And so the landscape of possible attacks is very broad. Okay, so in this whole context, about 10 years ago, there was renewed interest in this topic of trusted execution environments, also called enclaves. And one of the catalyzing factors was Intel bringing out an extension to the x86 instruction set called SGX, Software Guard Extensions. And then that was followed by all the other companies bringing their own solutions and open source solutions also coming up. Okay, so what are enclave platforms? I'll describe this in contrast to the traditional picture. So the traditional picture is here on the left, where you have your standard operating system running on hardware on top of which may have an intermediate microcode or firmware layer. And it's the job of the OS to provide isolation guarantees between applications. So the blue application is trusted, let's say, the black applications are not trusted, and you want to make sure that the blue application's execution and its secret data remain secret from these other applications. And to do this, you have to trust everything else in blue at the bottom, right? Which is a problem because these are very large pieces of code. So the promise of trusted execution environments is that you can take out large chunks of the system stack out of the TCB, the trusted computing base, right? So the OS is no longer trusted. And what you do instead is you have a root of trust in the hardware. And so you want to make sure that the hardware will provide some security guarantees, some primitives, and you build a small software or firmware layer on top of that, and that together forms your trusted computing base. And that provides isolation guarantees to these applications that we'll call enclaves, which are essentially regions of code and data that are by the hardware and firmware guaranteed to be isolated from everything else. Okay, so there's many examples of this that have emerged over the last decade, including some open source ones that are based on RISC-V. Okay, but that's the promise, right, of trusted execution environments. Simultaneously, we've seen the vulnerability landscape grow. So of course, we've had the standard software attacks like Heartbleed, Log4j, etc. We have, of course, there's always been interest in looking at hardware vulnerabilities and Trojans and things like that. But what has grown really is the stuff in the middle. So about 5 years ago, there was an awareness that a lot of the features that make modern microprocessors efficient, like speculative execution and so forth, are vulnerable to attack. Right? So things, the attacks like Spectre and Meltdown kind of brought this to the fore. And what made this interesting was that these are attacks that involve hardware features, but they're exploitable through software, right? And so that makes it a much more accessible thing as opposed to more invasive hardware attacks where people are doing like differential power analysis or things like that. So this middle part, this heterogeneous threat landscape, is the thing that I'll be focusing on mainly in my talk today, right? And how do we deal with that? So the central question that our work has been trying to address is how do we efficiently formally verify that these trusted execution environments provide the required security guarantees in the face of these kinds of heterogeneous hardware software threats. Okay? And so in my talk, I'm going to touch upon all the bolded phrases, the 4 bolded phrases that I have in this question. Okay, so here's the outline for the rest of the talk. So first, I'll talk about formal modeling and verification of these trusted execution environments. Then I'll, in that initial work, this is work in the beginning that I'll tell you about that we did around 6-7 years ago using sort of existing state-of-the-art tools for formal modeling and verification. And that project led us to understand some of the limitations of these tools. And so we then designed our own verification system called UCLID5, so I'll tell you about that. And then I will tell you about a much newer work which was published just last year that picks up on our earlier work and shows how UCLID5 can be used for modeling extensions of trusted execution environments that have happened in the last 2-3 years. But doing it in an incremental fashion, so we kind of reuse a lot of the work that we did back in 2017 as well. And then finally, I'll talk about how UCLID5 can also be used for reasoning about these kinds of heterogeneous threats like Spectre and Meltdown, which come under the general heading of transient execution attacks. Okay, and then I'll conclude and talk about future work. All right, any questions before I dive in? Okay, Good. So I'll talk about the formal modeling and verification first. So like I said, this is a work that we started doing back in late 2016 and early 2017, and this was work that was led by my former postdoc Pramod Subramanian and former student Rohit Sinha in collaboration with Srini Devdas at MIT and his group. All right, so here's the setup again that I showed you earlier. So you have your user who is sitting on one side of the network and interacting with an application that's running on a server, except that this server is has one of these trusted execution environments, right? So it's running, your user is interacting with the application in an enclave which has these stated guarantees like SGX provides from the enclave platform, and it's running in the context of untrusted applications and an untrusted OS. Okay, and so if you recall, I had these questions at the beginning, right? Like, does my secret data remain secret? Am I executing the right program, and is the program doing what I want, right? And so in this paper, we address those questions by first trying to formulate a property, a formal specification for what secure remote execution means. And then the second thing we did was provide a formal model for a trusted execution environment, an enclave platform. And then the third thing we did was try to verify that our formal model satisfies the secure remote execution property. Okay, so those are the three things. Right. So so just to reiterate, I'll tell you about the formal definition of SRE. Also, how we can decompose that into three more easily checkable properties. Then I'll tell you about the formal model very briefly, and then the results of our formal verification. Okay. All right. So so first, our formal model is based on sort of a standard way of modeling executions as traces, where we're looking at the enclave program's execution interleaved with actions of the adversary, right? And so here's a trace in this. Let me just use my mouse so people online can see as well. So every dot in this trace is a state, and the edges are operations that take you from one state to another, the transitions. And so this is one trace, one execution. So here what you do is you launch an enclave, initialize it, then you enter and start executing the enclave. At some point you exit, and then you resume, you execute something else, then you enter again, exit, etc. So these are, I haven't colored the arrows, but there are some arrows that are actions of the enclave under consideration, and there are other arrows where there are actions of other processes that are running on the system. So let's say the enclave is called E, and brackets E is the set of all traces. So it's denotational semantics for the enclave E. Now, to model the adversary, the way we formally model adversaries is through two operations the adversary does. So the adversary is a process that can execute at any point between operations of the enclave, and you have to choose some level of atomicity for this. But when the adversary executes, they can do two things, and they can do it, you know, in an arbitrary fashion for an arbitrary length of time. So the first thing is called the tamper function, which is they can execute any operation on the platform that's available to them. So you can think of it as executing any instruction operating on any region of memory or CPU state that's available to them. And the second thing is the observe function, which is you can define the entire state of the platform, which is the state of the CPU, the state of memory, and so on. And then the observe function basically is a projection from that state to the observable part for the adversary, right? And so that's what we call a privileged software adversary. So for every platform, you have to define what these are. And so then, given those two things, the SRE property is the following. Okay, again, the paper has it more formally, but this is in more informal words. Yeah.
So, when you enter a enclave, you're allowed to execute any instruction. There is no instruction set.
Yeah. So you can. That's right. The enclave can execute some number of instructions, and then of course the OS scheduler can.
So inside the enclave.
That's right.
Are there limitations on what
You can execute any instructions, yeah. And of course, if you execute the SGX instructions or enclave operations, then they may have some effect on the execution of the enclave in terms of pausing it or exiting the enclave, depending on what operations you execute. Right. So I'll tell you a little bit more about the operations after this, but at a high level idea, the enclave is like any program, right? So it has available to it the entire instruction set, and we are really, in this case, we are modeling the ISA level semantics, right? So thinking of program executions as sequences of instructions. Yeah, question?
You've been only looking at one enclave at a time. It takes something more you want that.
No, so yeah, so what we are doing, what I showed you there is the execution of one enclave interleaved with everything else. Okay, so we just conservatively assume that everything else is untrusted here, right? And so you can think of a trace as being black arrows and red arrows. Red arrows are arrows by adversaries, and black arrows are the
So I'm just trying to see if there is any composition reality you need that looking at each one being secure separately.
Yeah.
Apply the ideal behavior that you expect when both of them are secure, right? Because when each one is secure, you're assuming address is allowed to happen the other.
Correct. Yeah. So it's a good point. So I think there's this well-known understanding that these kinds of security properties like non-interference are non-compositional in general. But what I'm saying here is I'm trying to formulate a property from the viewpoint of a single enclave, right? And so for that reason, I'm just going to consider an execution as being comprised as interleavings of operations of E and other operations. And so, yeah, and now if I want to write a property that involves multiple enclaves, I could then, refine my notion of a trace and define a property based on that.
So in this picture, you see each of these dots in the state, but state contains something which are internal to the enclave.
Correct, exactly. And here, I'm not making that distinction yet. Later I will. Okay? Yeah. Okay. So yeah, so what is secure remote execution? It's basically what's stated here, which is that first of all, so if I execute my enclave on a completely trusted platform, and it's the only thing that runs, then I compute the set of all traces, and there's a bracket C. So now what this is saying is any execution trace on the remote platform should also be in that set. There should be nothing that is outside that set. Okay. So that's the first point. And the second point is the adversary running on the remote platform, their observation, what they know has to be restricted to what they can gather from the observation function. Okay, which is again a projection from the state of the platform to what is observable. So in our CCS 17 paper, what we specified was that this property is actually if you look at this property, it's not something that one can easily verify because it's based on this more abstract notion of a set of traces, right? Like trace containment. I want to check that all executions on this remote platform has to be contained in the valid set of traces on a completely trusted platform. So what we show is that you can actually reformulate that property as a conjunction of three other properties, which we call measurement, integrity, and confidentiality. And again, here in this talk, I'm not going to get into the details. So what measurement does is it says that we are executing the right enclave. So this is more of a cryptographic property that is based on the attestation function that trusted execution environments provide. But the other two properties are versions of what is known as observational determinism in the literature on specifying non-interference style properties. So the first one is basically saying that is an integrity property which says the adversary only influences enclave execution through inputs that it can provide to the program. And the confidentiality property, all it says is the adversary knowledge is limited to what it can observe. So again, I think going to Supratik's question, you can take your state and you can divide it up into state that is observable by the adversary and state that is not observable to the adversary. And what this property is basically saying is that is the standard thing in non-interference style, which is that if I look at two traces where the secret state can be different, but the public state that the adversary can observe is the same, then that the adversary's observation remains limited to the public state throughout the trace. So there's nothing new here. It's just basically just these are properties that are based on the standard notion of observational determinism, right? But what we show in this paper was that this seemingly more complex property can be checked by just checking these three properties, that they imply the top one. Okay. So so this is all a little bit of background. So I'm going to go a little fast through it, but if you want more details, I'm happy to talk about this offline. The second thing that we did in this work was modeling this trusted abstract platform, right? So so what does a formal model of a trusted execution environment look like? So what we wanted to do is come up with a formal specification of a trusted abstract platform that abstracts away from particular implementations. So we want it to be applicable to Intel SGX and RISC-V, Keystone, and so forth, but yet be something that is more abstract and devoid of the specific instruction sets, right? But it should also include an adversary model and be able to be something that we can reason about this SRE property on. Okay, so this is what it looks like. So the TAP model, first, it's in the formal method sense, it is what is called as a transition system model, where we'll define some state and then we'll define operations that correspond to transitions on that state. So the state is just what you would expect. There is CPU state that includes also the memory. Then there is some state associated with address translation, which is so we have to model the details of how the system manages virtual to physical mappings and address allocation and things like that. And so we need to have that state, and then we have to model state that is specific to enclaves, so metadata for enclaves. And then on top of that, we have essentially 5 categories of operations. Okay, so on the left, we model the memory operations, sort of standard memory operations. And the main thing to think about here is these models are essentially saying, you can think of them as extensions of ISA level descriptions, where in an ISA specification for x86, let's say, you would say what a load does, what a store does, etc. And here we would do that in terms of its impact on the abstract CPU state, but also in terms of its impact on these two things, right? So in typical ISA level specification, you would not specify the impact of those operations on microarchitectural state or other metadata, but here we do. Okay, so that's the thing that happens in these models. So we model the memory operations, we model page table sort of operations relating to address translation, and then all of these operations are relating to the enclaves. So there is an operation that corresponds to creating an enclave and then tearing it down. Then there's an operation that corresponds to entering an enclave, exiting an enclave, temporarily pausing an enclave and then resuming it, and then finally computing a cryptographic hash. Okay, so those are all the models, the operations that we model here. And so now you could imagine any program as being a program that has available to it all of the standard instructions plus all of these operations, enclave operations as well. Okay, so now what this becomes is similar to the ISA. It becomes like a hardware-software contract, right? It becomes an intermediate specification where what we can do is we can take more detailed models of specific implementations of trusted execution environments like SGX or the RISC-V Sanctum and so on, and we can check whether they conform to this trusted abstract platform or the TAP specification. And then for enclave software, we can use the TAP specification as a model of what a typical trusted execution environment would provide, and do verification of the enclave software with respect to that, right? So it becomes like an intermediate specification. Okay, good. So the other thing I haven't talked about is the adversary model here. And so what we did was to consider kind of a fine-grained adversary model where we have three kinds of adversaries. So the first adversary, so all three of these, so we call them M, C, and MC and P. So the M part corresponds to memory operations. C means cache, and P is paged. And so the idea with these models is that the adversary could essentially be any program that invokes any of these tap operations plus any instruction in the instruction set. But in terms of what the adversary can observe, that is different amongst these three. So in the top case, the adversary can only observe regions of the memory that they are allowed to. In this case, you think of cache as a side channel, and in this case, we assume the adversary can also look at the page table state. Okay, and so what we were able to prove, and I'll say in a minute how we did this, but what we were able to prove in this was, first of all, we checked whether this formal model satisfies the secure remote execution property, and so we were able to show this in most cases except for two, right? And so what we ended up finding issues were things that were actually known, that with SGX, right? So SGX, this is, I think, SGX version 1 at the time, was secure for an adversary that satisfies SRE for an adversary that can only observe memory regions, but not if the cache sets had sharing, right? So amongst processes, and similarly, not if the page tables also could be observed. Okay. Yeah. So TAP is a specification for the real hardware, right?
So then on top of that, to achieve secure remote execution, you need to use TAP in a particular way.
So TAP is like a formal model, and then you have to check these three measurement, integrity, confidentiality properties on this formal model, right? And so these are all what are called two safety properties, which means the way you typically do this is you make two copies of your system. You compose, it's called self-composition, and then you can run a model checker to essentially explore the executions in parallel and check whether in these two copies, if their private state, the secret state is different, you want to check that the adversary cannot tell that the public state the public state should also be, if it started out equal, the adversary cannot tell the difference in these two executions.
So on top of TAP, I will be writing some program.
Yeah.
That program as well.
Correct. So I'm not talking about the correctness of that program here. So here I'm just talking about whether the platform the platform model satisfies this property. Okay, and so at this point this has no connection with any particular implementation, the TAP specification itself. So let me give you a diagram that may show exactly what we did. So there's a formal model that we wrote by hand. This is the thing that I was just talking about, whether that formal model satisfies the SRE property that I talked about earlier. Then there is specific trusted execution environment. So there's Intel SGX, and then there is the MIT RISC-V Sanctum processor, right? So these back in 2017 were models that we also created by hand, but looking at the detailed specification of SGX and the specification, the code of Sanctum in our case, and then these are refinement proofs. So we're basically trying to check that every transition of this can be mimicked by the TAP model, and vice versa in this case. So these refinement checks are the connections to the specific platform implementations, although back then these were also models of SGX and Sanctum respectively. Right. This is basically saying this model of trusted execution environments will satisfy this property, provided with respect to some adversary models, provided some side conditions hold, right? And so that's the kind of proof that we have here. Okay.
So irrespective of what program is running, remote execution.
That's right. Yeah. So this is basically exactly, yes. So this is basically agnostic to the what is running on the trusted abstract platform, right?
So what I meant is,
Yeah.
wouldn't there be something to say that coming out of this tab, the message should be encrypted, or so that the adversary cannot observe it?
Yeah. Okay. Good. So good question. So I've totally abstracted the crypto parts here. So the way we model the crypto is using the perfect cryptography model, what is often called the Dolev-Yao model, which is that we have axioms that formalize what the cryptographic operations semantics are.
So the physical observation units is certain things cannot be observed.
That's right. Yeah, and only if you have the key can you decrypt it. So again, this is all standard stuff, and so we just write these axioms down about the crypto operations and we use them.
So is that part of the tab?
That is part of the tab, exactly. Yeah, that is part of the tab. That's right. Yeah. And also one more thing, so it was a good question, you good asked this question, that so this verification is for all programs that run on the tab, but there is a model for how the programs are written, meaning that they have to execute the operations in a legal order. So for example, enclave operations, like certain operations have to follow certain other operations, and we enforce that, right? Yeah, so that's, yeah.
The SGX has lots of vulnerabilities.
That's right, yeah.
And also lots of countermeasures. If you take a vulnerability
Yeah,
and a countermeasure,
yes,
is it possible to prove in your system
yeah.
that the countermeasure indeed works, or it works only sometimes?
Yeah, so that is actually coming towards the end of the talk, and I might be a little pressed for time, but yes, the answer is yes.
SGX is out of support by Intel. What is the correct?
That I don't know. I mean, there's a lot more talk on TDX and so forth, but there is, I think, more interest. So I think on the enclave side, there's a lot of activity on software-only solutions for
problem
enclave.
Is the operating systems.
Right.
It's only one connection you can do.
Right.
But if it has to be interacting operating system,
Yeah.
problem comes into the picture.
That's right. Yeah. And on the RISC-V side, so I think there are open source enclave platforms. All right. So one thing here is that all of this work that I talked about was done using the Boogie verification system from Microsoft Research, which was not something that we did, but it took us a lot of effort. So it ended up being a fairly manual effort, in spite of the fact that Boogie is supposed to be a push button verification tool. And so there were some lessons that we learned from this. The first one was that this area of trusted execution environments is a little unique from a verification perspective, because it's a combination of hardware and software, and up until then the formal verification tools were either geared towards software or geared towards hardware. So Boogie in particular was something that was written for sequential software, but we had to model hardware components and concurrency and things like that, and it wasn't a very good match. The second thing, of course, was, as you saw, there were 4 person months required. There was a need for a lot more automation in terms of generating invariants and strengthening them and breaking up the proof and so forth. Okay, so that's from this effort, what we came away with is that we needed really.
What kind of a inductive invariant
Yeah.
look for in a cloud computing?
So this is again. So let me answer your question in 2 parts. In a cloud computing setting for distributed protocols, of course, there are inductive invariants that you might write for that. Here, this is not like that. This is just a platform verification problem. So the inductive invariants that we had to write here had to do with properties on who can touch what regions of memory after the steps. Like for every operation, the launch, destroy, etc.
I may not know what is the software that is being launched in the cloud.
That's right.
How do I know?
So this is like I said to Manoj's.
They give a PCC kind of.
Exactly, but this is, so as Manoj was saying, this is agnostic to that. We're not talking about specific applications. We are modeling these platform operations, like what it means to launch an enclave and to destroy an enclave and enter an enclave. Each of these operations has some preconditions and postconditions that it must satisfy. And now we are looking at an execution that is an interleaving in all these operations. So on every transition, if you are running launch, certain conditions have to hold. If you're running enter, certain conditions have to hold. So your invariants have to encode those conditions.
That
right?
means it will work for class of transactions. Right?
So this will work for the operations in this trusted abstract platform, in this trusted execution environment model. That's right. All right. So let me just do a quick time check. How late can we go, Supratik? Okay. So let me wrap up at 12:15 then. So if I can have half an hour more, then I can cover stuff relating to the questions that were asked. Okay. So this actually connects up to some broader trends in formal methods that we've observed. So one of these trends is that that I talked about is already this hardware software flavor. So these are systems are more heterogeneous, and you need a modeling language that can capture this. So actually, Professor Shamsundar just talked about distributed systems, cloud services. There's been lots of work on protocol verification, but if you look at the way in which the protocols are typically modeled, it's very high level and abstract, often in logic. But if you look at the implementations of some of these protocols at AWS or Azure and so on, there's a lot more detail, implementation level detail that the abstract versions don't have, and often the bugs are there in the implementation detail. And so,
particularly for the properties you said,
yeah,
privacy and confidentiality,
yeah,
you have to trust the cloud service provider to say, I'm doing this.
that's right. Yeah. So, but the point is that these are the type of heterogeneous systems where you have to model detailed software level details in addition to protocol interactions. So I think the other thing is, of course, the need of automation that I talked about, and the third is more recent, which is I think there's been realization that you can, by using data-driven learning from data that you get from running test cases or simulations and things like that, you can synthesize invariants that you can then use in the verification process, or you can basically generate guesses for proof artifacts that will speed up verification. Okay, and so so one of the things we need to deal with for heterogeneous systems is to think of not just one way to do formal modeling and specification, but multiple ways. And then we need to have techniques to automatically synthesize these things like invariants and compositional proofs, and then use learning in the process as well. Okay, and so this is something that I started working on back in 2012, and even before that. And then finally, after Pramod joined my group, we created this new verification system to address the limitations that we saw in our initial TAP verification project. So that's UCLID5, and it's an open source tool that we've been developing over the last 5 years, and which I'll be talking about more informally in the afternoon. Okay, and so let me tell you a little bit. It's a bit of a digression on UCLID5, and then I will. That's right. Yeah. That's right. So Pramod and I started this UCLID5 project with some of my other students, and now the most recent work on that was something that we presented at CAV last year. So now UCLID5 is an effort that has many of my group alumni as well as our students working on. So it's like a multi-institutional project. Okay, so the genesis of UCLID5 is actually going back to a system that I created for my PhD along with Randy Bryant and other colleagues at CMU, called Euclid, which was one of the first satisfiability modulo theory solvers and verifiers. And so the idea in Euclid was that you basically, as opposed to just modeling software and hardware at the detailed level in terms of bits or bit vectors, you raise the level of abstraction by using first order logic with suitable background theories. Okay, and then we showed many applications both in hardware verification and software verification and protocol verification. Now, if you are not working in formal methods, let me give you a more high level view of the spectrum of verification tools. So on one end, the spectrum is a much less automated, more manual approach to verification, which is based on things like interactive theorem proving. So systems like Hall, Coq, and so forth. On the other end is very highly automated verification techniques that are based on simulation or testing. And so UCLID5 is very much in the middle, right? So it incorporates ideas from symbolic model checking, and it also incorporates ideas from Floyd-Hoare style program verification in one system. Okay, and so so what do I mean by multi-modal modeling, specification, and verification and synthesis? Okay, so the first thing I want to say is in terms of the model, the UCLID5 model, you can model systems with different approaches. So one approach is axiomatic, that is very declarative. You just write logical formulas to model your system. The other is more operational. You think of a system as having state and transitions, and so you basically model the details of how the state gets updated, right? This also relates to having a transition system model which is quite common in verification. But if you look at software often tends to be more procedural. You have essentially a procedure with a precondition and postcondition, a sequence of statements, and so on. And so typically for software verification, the kind of modeling that people use is procedural. For hardware verification or protocol verification, people use transition systems, which is well suited for modeling concurrent interactions. And but then if you want to model both, what we've seen is you need a modeling language that allows you to do both of these things. So that's something that you can do in UCLID5. You can do all of these things in the same language. The other thing we noticed is that specifications are also quite heterogeneous in this kind of system. So if you have a program, you might want to just put assertions in your procedure and check those assertions or loop invariants, right? And that's sort of the standard model for a verification tool like Boogie. If you're doing hardware verification, on the other hand, you might be writing properties in temporal logic or specifying invariants. If you're doing security verification, you might be writing hyper properties. And so there's really a range of different specifications, and the tools were only allowing people to do one or the other or a few of these things.
Why did you not integrate by simulation?
We can do by simulation too. I didn't list it. So you can also check simulation and by simulation.
Just a complementary definition.
That's right.
Semantics and operation.
That's right, yeah. But it actually makes a difference in terms of how the underlying algorithms work.
The abstraction, it all depends.
But also the algorithms that work. So for example, if you think look at model checking algorithms like property directed reachability, PDR. Those algorithms are typically only defined over operational models. You have a transition system and you take updates and so on. Now if I have a fully axiomatic model where I have traces and I'm just imposing properties on traces, I have no way to essentially do model checking based on PDR on that model. But in some sense, as you said, semantically there is no difference. Like if I write an operational model, I ought to be able to translate into an axiomatic model and vice versa, right? So with our approach, you can do that. Whereas,
but if you don't give it, you don't have a sounded complete.
If you don't give, don't give what?
You can only show if you say axiomatics whether it is complete.
Yeah.
You have to have an operational model. Otherwise, it's very difficult to bring it with respect to the underlying transition system.
How you mean how?
Like a semantics is complete with respect to the.
Yeah. So in this case, we are not really verifying the semantics per se, right? What we are doing is we're trying to model a particular system, and the axiomatic approach is basically the trace theoretic approach, which is saying the system, I'm going to model it as a set of traces, and I'm going to impose properties on those traces, right? So that's what I mean by axiomatic. Okay. There's also a range of different proof techniques people use, but the one thing I want to highlight here that has come up in more recently is the how you actually do the verification. So a lot of verifiers now rely on SMT solvers, but there's been realization that you can automate the generation of proof artifacts, including things like simulation and by-simulation relations, invariants, and so on, through the use of ideas from program synthesis. So that's what this is, syntax credit synthesis. And so in UCLID5 is I think one of the first tools that not only integrates SMT but also these synthesis solvers. So you can yeah, I'll say what that is. But the idea here is that this is a syntax-guided synthesis is essentially an encapsulation of the common program synthesis techniques in a backend solver. So you can basically say, here's a program, and I want to prove this invariant, but I know it has to be strengthened. I don't know exactly what the strengthening is. So synthesize the strengthening for me if it exists. Right? So you can basically, rather than manually writing down the strengthenings, you can farm it out to a synthesis solver. Okay, so coming to Akshay's question, right? So SIMO and SMTO, these things I lectured about in the winter school last December, but SMTO is SMT with oracles. So this is an extension that we've done in my group in the last 2 years, where you can take an SMT solver, and one of the limitations of SMT solvers is that everything has to be encoded in logic, right? But there are some problems where encoding something in logic might be undesirable. For example, I'm verifying a program that uses a library, and that library is too messy for me to encode into logic. But I would just like to treat that library as an oracle and invoke the oracle on an on-demand fashion from within the solver to build a model that will allow me to prove or disprove the property. Right? So this is what this is. So SMTO is an extension of SMT where you have this kind of ability to query external oracles. And SIMO is an extension of syntax-guided synthesis with the same thing, where you also have these external oracles. Okay, so if any of you are available in the afternoon, I can actually demo these things to you. Okay, so in the interest of time, I'll skip over this. And so UCLID5 has been applied to many of these domains. And in fact, I gave 2 tutorials on UCLID5 last year. All the material is available at that URL. But coming back to this trusted abstract platform model, right? So what we did was, recall we originally did that work in Boogie. We repeated that modeling and verification in UCLID5, and we can see, there are improvements that you can obtain. Particularly, the verification time of some of our proofs went down substantially, and partly because the encodings of the models were much more compact in many ways, and the number of annotations that you needed to manually specify also went down. Okay. All right. So now I want to come back to the trusted execution environment setup, and so this was basically applying UCLID5 to the old problem from 2017, right? So same model but porting it over to UCLID5 and repeating the verification. Okay, so last year we did a different case study. So some of my colleagues at Berkeley were working on a RISC-V based enclave platform called Cerberus, which goes well beyond the original vision of what an enclave platform is. Okay, and so one of the new trends in these trusted execution environments is that enclaves can share memory. Okay, this may seem counterintuitive because the original picture of an enclave was that it's a region of code and memory that is isolated from everything else, right? So, so why do you want to share memory? And so one of the reasons that I understand is really efficiency, that processes need to communicate, and one way of communication, of course, is through shared memory, right? But if your enclave is not allowed to shared memory, then everything has to go through there's a little bit of overhead for doing that communication, right? Everything has to go through the secure channels that introduce an overhead. So let me tell you what the landscape has been in terms of projects. So there have been, in the last 2-3 years, there have been many projects that are extending SGX style enclave platforms with sharing. So on the left is the original model. So you have 4 enclaves, E1, E2, E3, E4, and each of them have their own regions of memory, no sharing. Okay, so very restrictive. On the other side, you could imagine that all 4 of these regions have some amount of sharing, right? So region 4 is shared by E1 and E4, E3 and E4. Region 1 is shared by E1, E2 and E3 and so on. So this is a very relaxed sharing model. And in fact, there's an implementation called Elastic Clave that is doing exactly this. Then there's something that is a little less restrictive than that, which is called capped sharing, where you say, I'll bound the number of enclaves that are allowed to share a region at any given point in time. right? So here the bound is 2. And then, so there's a implementation like that as well. And then there's a yet more restrictive thing, which is saying single sharing, meaning that there's only one region of memory that can be shared, and everything else has to be like it was before, isolated. Okay?
So what is sharing of enclave?
So sharing is, so typically an enclave program has an associated memory region that is allocated, and no other process, not even the operating system, is allowed to read or write to that. That's the original model of the enclave. So the sharing model is basically saying, I'm going to define a region of memory that can be shared by multiple programs. So this is not talking about the cache. Yeah, the cache is assumed shared, right? It's a shared resource. It's a microarchitectural resource that is shared. This is just talking about the ISA level view of memory. Yeah, right? The logical view of memory.
Load all these programs together because I don't want to share with some program.
It's
That-
a partitioning of the memory.
That's right. So, yeah, exactly. It's a partitioning of the memory. And so, to answer your question, right, you don't need to load them together. You can kind of define this at enclave initialization time. Yeah,
If I want, I can.
exactly. And so there are operations that will allow you to do this, and I'll show you exactly what those are.
One limitation of enclaves, I suppose, would be that it's small. Does this allow you to kind of expand your enclave?
Exactly, yeah. So that's part of the reason. So the idea would be that you have your application and you can define multiple enclaves. So you have a big application, you partition it into multiple enclaves plus non-enclave code, right?
Information flow will be a problem.
It will be exactly. So that's the kind of thing we were looking at, right? Okay, so the Cerberus platform that was just done at Berkeley based on a RISC-V based enclave uses that single sharing model, right? And in the paper that we published together in CCS last year, there were two things we showed. So my colleagues who worked on this from architecture and security, they were interested in showing that it was expressive enough to support applications. But on our side, we showed that doing the design of Cerberus based on the trusted abstract platform specification made formal verification much easier. So it was sort of a design for verification exercise. Okay, so there are two new operations, TAP operations, called snapshot and clone, and that's what allows the sharing. So the sharing is very structured. It has to be done through these two operations. Okay, so the idea is, imagine that you have an enclave, and this is the enclave's view of its memory, its logical layout of memory, which may actually be laid out in physical memory in some way.
So this is essentially borrowed from linearization technique, snapshot and clone. If I have to show that I have a linearization possibility or work on the synchronization power technically.
Yeah.
If you don't have snapshot, which essentially
Yeah.
freezes all the
Yeah.
things to do that, which
That's
is
right.
a complex thing, right?
That's right. Yeah, that's an excellent observation. That's right. Okay, so right, so imagine at step 1, enclave E0's memory looks something like this, where there is it's got these pages that are laid out in physical memory somewhere, and then you do the snapshot. So at this point, enclave E0 ceases to run, but its state is frozen, right, and it's not discarded. Okay, so that's what snapshot does. It basically keeps a copy of that enclave state. Okay, and so now what the clone operation does is, you can have an enclave E0. If you do clone on this enclave, it will make a copy of its state and use that state to initialize a new enclave E1. Okay, but after that point, E0 and E1 will remain isolated. So the idea is basically you're using this clone operation to be able to essentially take the computation that one enclave does and share it and initialize a different computation. Okay?
But this will have restrictions. all functions you can't capture it by this.
That's right, yeah.
Because it is based upon the consensus numbers.
That's right, yeah.
And so it will fail in some of the things. Very difficult to find it.
Yeah, so you can't model all kinds of sharing, shared computations in this way. Okay, and then the third thing that you can do here is you can take kind of a hybrid of the first two. So you take your E0, you snapshot it, and then using that snapshot, you initialize a new enclave. So right now E0 is not running, but you clone that state and you run E1. Okay, so that's the kind of thing that you do with snapshot and clone. And so now what we did in the verification side was we took our original TAP model and we just extended it with these two operations, right? So clone is basically in this family.
Clone,
yeah.
It would essentially correspond to an STM, software transaction.
Mm-hmm.
If many of them are executing, do you also prove the opaque property?
So can you elaborate? What is the property you have in mind?
In some sense, I will have to capture at what point this can fail.
Okay.
If there are independent things that are happening, if I have to go back on the distributed snapshot, I have to go
if
back
I
to
want
the
to,
point where everything will remain the same, because only one of them is chosen, rest of them are thrown out.
Yes.
Then I have to go back to that state. For that, if I have to know, I have to show that property, opacity is important thing for STM.
Okay. Yeah, I have to. I don't think we looked at opacity as a property in this context, but that's a good point. Yeah, especially so again, STM was not really a focus in this particular work, but it's a good point that you make. Yeah. All right. Okay. So from a verification, so there's much more in the paper on what applications can be run, but I'll just talk about the verification side of things. So what we did was we took our original TAP model, which I talked about earlier in UCLID5, and then the revised model, which we call TAP-C, and two things what we looked at. So first thing is whether the model size grows, and in this case there was only kind of moderate growth in the size of the formal model in UCLID5 because you were just adding these two operations. Of course the operations themselves were quite involved. And in terms of the verification time, most of the time was in the solver end, in the Z3 SMT solver. And there was, depending on what proofs we were doing, there was an increase in runtime from 3 to 8 times in the verification time. But overall, I think the main takeaway for us was that this was a much faster process, that we were able to do a more incremental proof, take our original UCLID5 model, not really change a lot of what we had before, but just add these operations and then focus on proving the invariance on these additional operations. So I think from that perspective, I think if you compare it with other verification projects like Cell 4 that was done using interactive theorem proving, what I've been told by those teams is that the amount of work it takes to port the proofs in Isabelle, Hall, or of these theorem provers, if you make changes in the underlying model, implementation, is really in person years. It takes a long time to port those proofs over because everything was done manually. Whereas here, since a lot of things were automated, it's much faster and something that we can maintain more incrementally. Okay, so now in the last 5 minutes, I'll just give you a brief overview of using UCLID5 for reasoning about transient execution attacks. Okay, so I'm going to go over this quickly because I'm assuming everybody knows what transient execution attacks are, right? So the Spectre meltdown family of attacks that essentially exploit microarchitectural level transient state updates, right? So speculative execution is a good example of this, where you might, if you have speculative execution, then the branch may be predicted one way, but it's supposed to be executed another way, and then the processor goes ahead and goes down the wrong path, and there are microarchitectural updates that happen even after the rollback that an attacker can observe. Okay, so I'll just skip over the example quickly, But the problem that we were looking at is the following. So we are given a platform model, which is like, it could be something like TAP model if you're talking about trusted execution environment, or it could be just a standard processor description. You're given an adversary model, which is the tamper and observe functions, and a program, okay, something like this. You want to determine whether the program is vulnerable to a transient execution attack that is specified by that adversary model on that given platform. Okay, so this is really in a way you can think of it as a software verification problem. I'm given a piece of code. I think it's going to Manoj's question at the beginning, right? So now I'm not trying to do verification agnostic of what program runs. I'm actually given a particular program, and I want to check whether that program is vulnerable to this kind of an attack on a given platform, right? That's the problem. And so, for example, these two programs are taken from a library of small test cases that was written at the time when Spectre and Meltdown came out. Right? So the first one is vulnerable to Spectre variant 1. The second one has a memory fence that eliminates that vulnerability. Right? So you have a tool that for the first program says yes, it's vulnerable, and here's a counterexample. For the second program, it says no, it's not vulnerable. Okay.
What is in the second program?
So there is a memory fence that essentially makes sure that you don't speculatively go and execute that.
You can't go.
Yeah. Okay. So, all right. So what did we do? So in this case, one of the contributions. This work that was published at the Computer Security Foundation Symposium back in 2019. So the first thing we did was formalize a property that captures this notion of secure speculation and more generally transient execution attacks. Okay, so that's the first contribution. The second was essentially a model of the adversary for this class of attacks, and the third was to use UCLID5 for that. Okay, so I'll just talk about the property because I think that's the main intellectual contribution that I want to focus on here. So I mentioned this observational determinism before. This is just a standard formulation of non-interference where you have two traces, pi1 and pi2. The public or the adversarially observable state is the same in both cases, but in the first trace you have the blue secret, in the second trace you have the green secret. And so the observational determinism property states that from the viewpoint of the adversary, the executions are a deterministic function of the public state, right? So the adversary cannot tell the difference between these two and cannot observe that this is the blue trace and that's the green trace. Okay. Now, what we did in this paper was we formalized secure speculation as a generalization of observational determinism in the following way. So we look at the first two traces, which are these green traces, which are non-speculative traces. Imagine you had a processor and you turned off speculative execution, right? So then you get these green traces, but they still are similar to the previous slide. The top one has the blue secret and the bottom one has the green secret. Okay, and assume that the adversary cannot tell the difference between these two traces, right? So if observational determinism holds in the non-speculative context, then we want it to hold in the speculative context as well. Okay, so the secure speculation property basically says that if there was no information leak when there was no speculation, no speculative execution, then there must be no information leak even when speculative execution is turned on. Okay, that's what the property states.
Repeat this statement?
Yeah, if there is no information leakage to the adversary without speculative execution, then there is no information leakage with speculative execution.
So if you go back to the Spectre attack,
Yeah.
that is what happens, right?
So in the Spectre attack, if you turn off speculative execution,
Turn off the speculation.
yeah, which is what the memory fence was doing effectively, then there is no information leakage. But when you turn it on, there is. So this property would be violated by that.
This is non-compositional.
This is non.
Of values.
Uh,
Even composed with another process.
I think
Because
it's
based on values.
Yeah, but this is true for all of these types of properties, right? So we're not solving. We are not solving the non-compositional problem here, right? So we are taking a more monolithic approach to verifying these systems. Okay. All right. I'll just skip over that part as well. So what we did was that our adversary model, well, again, as I told before, there is an observation function and tamper function. And the adversary is a process that can execute an unbounded number of instructions in between any two instructions of the program, the victim program. And then we define what is observable. For example, in the case of Spectre variant 1, you're looking at the cache as a state that is observable. In other variants, there are other things like the branch target buffer or other microarchitectural data structures that are observable. And similarly, the tamper function, you could say that in the Spectre variant 1, what the adversary can modify is the state of the branch predictor to make it go down a path. Okay, so all of these things, like the observation function and tamper function, what we do is we define it more abstractly so that it applies not only to a specific variant of Spectre but to a whole family of those kinds of attacks. And then the way it's verified is this tool called Vector, which basically works at the instruction level. So it takes a C program, which is the victim program, and turns it into an instruction level representation. And then it takes models of the platform and the attacker in UCLID5 and verifies whether that secure speculation property holds. Okay, so that's what it's doing. So you can think of these as sort of a hardware model. This is a model of another process. This is a software model. And so you're able to have this combined hardware-software modeling in UCLID5. And then if it's insecure, get a counterexample. Okay. And so what we did back then was we took the original list of 15 C programs that exhibited a lot of these vulnerabilities. And then we used bounded model checking to find those vulnerabilities using UCLID5. And then we use induction to verify the absence in the presence of some mitigation. And so all of these run pretty fast. So I think the high level bit here is that formulating the right property was important, right, for us to be able to find these. And in contrast with a lot of the other approaches, our approach is more semantic. So a lot of the other approaches in the literature are syntactic, meaning they look for certain attack patterns. So one of these examples is this tool called Checkmate, which came out of Princeton several years ago. And that is essentially based on formulating patterns of attacks of these things that you look for. So you kind of look for specific attacks, and you can, if you find them, you can say an attack is present, but you can't prove the absence of an attack. Whereas using this approach, you specify the secure speculation property in a more semantic fashion, and then the adversary model is what specializes it to particular families of attacks. All right. So with that, I will conclude. So some of the main points were trusted execution environments, I think, are a really promising technology, but formal verification needs to be done on these in order to fully realize their potential, right, so that we can really trust them. And then what we realized while doing that was that we need a new approach to verification for these kinds of hardware-software platforms and their security properties, which has been implemented in UCLID5. And so there's a range of other things that are ongoing here that I could not talk about today. So the first is this idea of synthesis modulo oracles that I touched upon earlier in response to a question. The second is actually going to Manoj's question, which is in our earlier work we had sort of manually created models of SGX and these other enclave platforms. But what we really like to do is verify whether the implementations satisfy the TAP specification. So we're actually working on that right now, and we have some initial results on using synthesis to essentially lift these models, Euclid models, from code. We also have work on verifying hardware security features. So there's a bunch of hardware level schemes for dealing with side channel attacks, like cache partitioning schemes. and we've been able to devise custom verification algorithms for these. And then there's some work we've been doing on scaling up the approach that I just talked about at the end through compositional reasoning. So being able to verify absence of attacks on much larger programs. Okay, and then the other thing I wanted to mention was applications of UCLID5 to other domains, not just security. So one thing is real-time embedded software that we've been working on, and the other is cloud services. Okay, so with that, I'll conclude here. Thank you. More questions? Yeah. What are the SMT theories? These are all bit vectors, uninterpreted functions, and arrays with quantifiers. So we model them with uninterpreted functions with axioms on them. Yeah. I mean, at the time we did all this work, UCLID5 did not have support for abstract data types. Now that is being implemented, and that might make some of these things easier. But other than that, I think my experience has been for a lot of these systems, software and hardware verification, this combination of bit vectors, uninterpreted functions, and arrays is sufficient, right? I mean, you don't need more than that. You do need quantifiers, but yeah. Because you know the architecture, or you can you specify something that is you could also, in some cases, in some models, you could treat this as an abstract type if you can just use uninterpreted functions on it. But yeah, but in many cases we know what the word size is. Yeah. Or we assume that we know what the model is parameterized by a word size. Yeah, I think we have some recent work where we have been able to find some variations of these attacks. Not so. Again, the way I would characterize it is that it is more model level attacks as opposed to. So there is still a step where you want to implement it and see if it is exploitable on real code. So that we have not done. But the nature of the attacks is very much similar to what was done before. So it's not like a fundamentally new attack. It's just a slight variation. Yeah.
So this hyperproperty, I mean, so there is now these logics on hyperproperty.
Correct.
Hyper-LTL.
That's right. Yeah.
Do you also?
No, we have not needed to use that because everything has been to safety so far. So it's yeah.
But is that something which you want to do? Or
Yeah, I mean, I think again, I think even my understanding is even those working on things like hyper LTL are looking for to specialize that, because the complexity of model checking for the general case is hard, and most of the properties are not really in the complicated part of hyper LTL, right? So actually, Pramod and his students had a nice paper at CAV 2020 where they were verifying a set of hyper properties, in part using UCLID5, but by encoding them to standard properties. So, right, and so they were basically, they were showing that you don't really need the heavy machinery of hyper LTL and model checking for hyper LTL for these things. So that's a CAV 2020 paper.
So, as a bottom line of looking at what's out there currently, SGX, or
Yeah.
do they meet your tag?
So we don't know for things like SGX. We don't really know, right? But for the RISC-V alternatives, this is something that that we have been working on, right? And I would say at this point we still have this implementation gap. So until we are able to check whether the implementations refine the TAP specification, the answer is we don't know. But yeah.
So we are happy with it as it is, or is there more like is there a need to strengthen that model, or that model is
I think the feedback that we have gotten on it is that it is sufficiently expressive model for these enclave platforms. So
for higher
yeah.
applications, it could just work with this path.
Yeah. So the idea with the TAP model was that if you have so all I've talked about today is verifying that the platforms, the implementation of these platforms meets the specification, right? But there is also a question of whether you write an application for an enclave platform and to verify whether that application, assuming the platform meets the specification, works correctly and does not leak secrets. And this could, something like this is important because you could write the application in a way that actually you're leaking confidence.
More kind of user-friendly, high-level abstraction, right? So as a person writing a program, I might think, I need this thread to have its own little processor. That's the mental model. Right? I need to, this enclave should be its own processor. In reality, it's not its own processor, right?
Yeah.
So, would you think, a high-level model that says we can create a secure process which runs on its own little Turing machine?
Yeah.
And then verify, if you took a program and did some compilation or,
Yeah.
some of
That's actually that is in fact, the enclave has its own little processor. That is really the model that is formalized by this integrity property, right? So it's like this two trace property I showed you earlier, right? But the idea is that you want to show that the enclave computation is a deterministic function of some trusted data and inputs and nothing else. And if you can show that, then it is basically saying that the enclave is essentially is as if it was the only thing that was running and nothing else was interfering with the execution. So the property itself has that inbuilt into it.
So
Yeah.
the confidentiality and integrity properties of TAP already is
That's right. Exactly.
it's as good as running as a
Yeah. And so what we did was to show that the platform satisfies those properties under certain conditions. But there is a question of, if I have an application, I may want to check whether the application has been written in a way, right, that it'll preserve, assuming the platform meets the TAP specification, that the application itself doesn't leak secrets, right? Which it could by just writing out to memory, right, without using the right operations. And so this is work actually that we did with Microsoft Research 8 odd years ago, before we did this work. So we assumed that SGX is correct, and we basically built program verifiers for x86 code that runs on SGX, and so that sort of effort required us to create a model of some model of SGX, which was specific to SGX. The TAP model goes a step beyond that by saying, now this is one thing that's more generic. So I can now verify a program. If I verify a program against the TAP model, then it holds for all implementations that refine that TAP model, right? That correctly implement that TAP model. And so I don't have to go and re-verify this for every hardware. So it's kind of, it makes the proof portable across platforms.
And the TAP model is better enough for
That's right.
programmers.
Yeah. So that's the idea. Okay, thank you.